All right, this is Bowei, 2016,
Yeah,
15.
16. Yes.
He worked on that query optimizer, and then Snowflake hired him right away because working in query optimizer is hard, right? And they love him there. It's Ellie. You graduated 2 years ago or a year ago?
1 year.
1 year ago. MCDS or no?
MCDS.
MCDS. She had a crappy intern. Oh, this is live. Hold on. She had an okay internship at some other company. She's like, I don't know what to do. Like, go talk to Snowflake. They do databases. She took 721, crushed it. And now you have the Snowflake. Well, you got the Dr. B hat on. That's okay. But you have the Snowflake shirt on. You're happy there. And this is Eli. He's the best database recruiter in the business. We like him. Okay. Snowflake is Snowflake. They're huge. All right, go for it.
I'll give a quick intro to company. We'll run through Andy's favorite part, which is our company slides here. So yeah, Snowflake, the data cloud, now going by the AI data cloud. You guys will learn about that.
You own Snowflake.ai.
Put that on the notes, please. We need to own that. I don't think we do.
I mean, we're not the lawyers here.
Yeah, that's true. Well, yeah, we'll get back to you. So quick run through agenda. We'll go through intros again. Andy kind of took care of that, so that's great. A little bit about each of us, and then we'll just dive into the technical content that we have. And Q&A is there at the end, but we definitely encourage in the moment questions as you guys are hearing what we have for you. So, so quick run through again of who we are. Obviously, Bowei and Olivia coming from the CMU family, but we do have Dan here as well, who's one of our principal engineers on our data pipeline and streaming team. Nikhil Shah, he's our senior manager running the streaming effort that we're doing at Snowflake. And then me, of course, from our UR team.
Cool. So I'm going to zoom out or up, I guess, raise the level of abstraction a little bit, down from like deep in the execution to more like the conceptual model that we provide to users of Snowflake and SQL in general. My field is continuous processing. I used to call it stream processing, but within the context of Snowflake, people actually don't. There are tons of use cases that don't restrict themselves to like a few seconds of latency, which is what usually comes to mind when someone says stream processing. And so really what we're talking about is like much broader, like people, it's okay if it's delayed by hours, maybe even a day or two. But the way they think about their data is a continuous flow. Even though, it's happening in discrete intervals, it's always happening in discrete intervals. The kind of mental model that we're trying to move toward is continuous. So you don't have to think about the scheduling and all the kind of minutia of how something happens. You just say what you want to happen. Like it's the classic kind of move toward declarative kind of semantics. And so I'm going to talk about the challenges that we faced with trying to make that possible within the context of SQL, and also like how we're trying to modify SQL to make that better. So as far as trends go, I already mentioned people want to think of their pipelines as continuous, and like declarative model of thinking about pipelines is kind of it simplifies the amount of work that people have to do when they set up their data pipelines. But even in this context, the industry trend is what you'd expect. There's always more data. Things always get more complicated. You make something simpler, and then the first thing that happens is people make more of it, and it gets complicated again, right? And then, of course, everyone's moving toward lower latency. So that's not to say that I already said that streaming is not the only kind of use case, but throughout this whole latency spectrum, everyone is shifting towards faster and faster. So people who used to do things on a daily basis, they're trying to set it up on an hourly basis, and hourly to a few minutes, and minutes is going down to seconds. There's additional stuff in like the milliseconds range that we currently aren't looking at. But you can think of this as like the whole distribution kind of shifting toward lower latency. In this context of data pipelines, a kind of trend that's really emerged as like the dominant way of setting up a continuous processing pipeline is incremental view maintenance. It's really nice. It has these benefits of being like really easy to learn. Everyone already knows SQL. And so all they have to do is write some SQL and ta-da, you have a continuous pipeline. And really, in principle, if the semantics are pure incremental view maintenance, you just kind of declaratively specified what you want to happen in your pipeline. And SQL being as like expressive as it is, that works really well in terms of like the amount of stuff that you can specify. And so there's a million examples of this. Within Snowflake, dynamic tables is kind of our solution for this. Materialize is probably the startup that's best known for this, like trumpeting this approach. When they came out in 2019, 2020, they were like, SQL is all you need. Like, why are all these stream processors doing all this garbage? I may be misquoting, but they were very vocal about it. And, they made a good point because, as I will say later, a lot of pre-existing streaming approaches have these awkward, inelegant solutions. There's also like Databricks as their Delta Live tables materialized view object that has the same thing. There's a bunch of startups in this field. So this IVM kind of paradigm is really kind of taking over the, cultural mindset. The problem is that it kind of falls short. It doesn't let you do everything you need to do. In my opinion, the reason for this is that SQL was designed as like a point in time kind of mindset. You have a database and you work on a snapshot. You have a transaction that like looks at some stuff, does some stuff, and then commits, and hopefully nobody conflicted with you in the meantime, right? That doesn't really translate cleanly into a continuous processing mindset where you really need to work across time. And there are SQL extensions for temporal databases and multi-temporality and stuff. It solves some of these problems. It does not solve all of these problems. And so we end up with these limitations that are not solved by multi-temporality, for example. If you imagine yourself, you're building a data pipeline that is a materialized view. Really, if you want some result, you need to have the source data. If you delete that source data, update that source data, it's going to propagate into your materialized view and it's going to change the result. And that actually is not what people want a lot of the time. You also, in kind of the same vein, you need to propagate these changes, or you need to have your pipeline ready to propagate these changes forever. And that means you accumulate a whole lot of state in the pipeline. A lot of the time that state could be worthless because you actually don't want to propagate these changes. And you end up recomputing stuff over and over again as inputs change. So an example of this, you might be doing like some kind of time bucketed aggregate, like you're calculating the average over per minute or something. And maybe some data trickles in over the course of an hour. You were kind of okay with the result. It's an average, right? It's converging to something. And it converged maybe in a few minutes, but you're still recomputing that thing over and over again while data keeps trickling in. And maybe it doesn't matter and you're paying for it. The other thing is, relatedly, you don't get a guarantee that the thing you're seeing is the thing you will see forever. There's no guarantee of this convergence or correctness. There's no obvious way, like, all of this can be implemented if you're clever enough and you go deep enough into the system, but you don't get signals about like the integrity of your data source. Very often, these data pipelines span a bunch of different teams. There's like your data engineering team and then some analytics team and then like business intelligence users. And way over here on the right side of the pipeline, they see something weird. Is it correct? Or was there just a delay way upstream in the pipeline, right? They don't really know. And so all of these problems are kind of intrinsic to the incremental view maintenance approach. Oh, sorry, I forgot the query evolution and backfill is like a very common workflow that data engineers will have where they kind of control exactly what gets computed when. And that's kind of a pain because you have to manually manage this, but it's also very expressive because you can say, oh, I changed my query. I want that change to apply in this point in time, range of time for these these keys. And you can kind of very fine-grained decide what you want to change. And so all of these things don't really work in an incremental view maintenance framework. And so I mentioned like other streaming systems have these kind of inelegant solutions to these problems. And I call them inelegant. Inelegance is really relative to something. So I'm going to be comparing it to the thing I talk about. But I would argue that these are all solving real problems. And they were, clever solutions within the scope of the problem that they were trying to solve. And so we have a bunch of examples of like the kind of solutions, like for not being able to retain all the data in the sources, you have these kind of append-only approaches. This is really well exemplified by the Delta Live table streaming tables. They have two kinds of objects. One is a materialized view with IVM semantics. The other one is not that. And it's like, why? Well, it's because of this problem, right? The need to expire state, both inside of the pipeline and all the way upstream, usually manifests in some kind of retention time. Almost every streaming system has this, but the semantics are usually not very well specified. And so you kind of have to be really careful about expiring your state correctly in a way that doesn't like, clear out state underneath business logic that you really cared about. And then it starts producing wrong answers and you don't really know why until you track it down to your retention configuration. The need to skip recomputation, I think, is probably best solved, is maybe an overstatement, but the triggers approach that Apache Beam and Apache Flink took kind of let you configure this, where you can say, I only want to recompute this every 100 elements or every 10 seconds or something like that. And it's very configurable. It's also super complicated to reason about, especially when you're putting computation downstream of these triggers. The lack of convergence, I would argue, has been pretty elegantly solved with the concepts of watermarks. The Kafka ecosystem has this kind of similar idea of grace periods, but those people have found watermarks and grace periods, I think, very difficult to reason about. I don't have tons of time to go into exactly what they are, but people think of them as like, 400 level advanced concepts when really they're fundamental to stream processing. And so there's kind of been a gap in understandability of what those concepts are. And then finally, for query evolution and backfill, most mature systems will have some kind of migration tooling that you can like write a pipeline that will process the state in your streaming pipeline and convert it into something else. It's a huge pain and it's very error prone. And new tools tend to come without this stuff because it actually is quite difficult to implement. And so all of these problems, I would argue, leave a lot to be desired. And the outcome of all of this coming together is the programming models are really complicated. There are these weird limitations that you only discover when you run into them. And like a lack of adoption in stream processing, I think, is kind of the way it's manifested in the market. So, I said all of these are problems relative to something else. I would argue that the something else is a new conceptual framework that can kind of try to unify all these problems and present a single solution to it. And if you sit down and think about it for years, like I and my teammates have, you find that there's this common thread between all these problems. And the thread is SQL is very powerful and it lets you express what you need, but it doesn't quite go the full distance. And the reason is because if you think of the SQL as specifying what you want all the time, you're overly restricted. But usually there was some point in time where the SQL expressed the result that you wanted. And so what we need to do is introduce some way to selectively decouple the semantics of that SQL from the time that you compute it. And so hopefully the way I'm phrasing this kind of leads you to the proposed solution here, which is immutability in some sense, configurable immutability. We call it a finalized constraint, which is a new kind of database constraint, where you give it a predicate, and based on that predicate, you say the table cannot be changed for any row for which that predicate is true. So you basically just like freeze a chunk of your table, and maybe that frozen chunk increases over time. And that lets you specify exactly when you want to kind of, you want your SQL result to apply. There's a dual concept to this, which is delaying your computation until the result is final. So you can think of these as finalized constraints apply on sources of data, and they kind of restrict what you can change. And final queries let you not compute things until they're done. And so you kind of get this duality of like preventing changes going forward and skipping changes until they're done. And you can kind of play with these two primitives in a whole bunch of different ways. So I'll pause here. I have a bunch of examples that kind of go through what the things you can express. And then at the end, which we probably won't have time for, I have like some interesting tidbits about how these can be implemented, but I want to pause for questions.
Yeah.
And I have a couple questions, unless there are questions in the room. Go take the room questions first, if
I
there
want
are.
the examples.
Well, that's next.
Yeah.
Okay, two quick questions, Dan, and maybe if it comes up in the examples, you could defer it. Do you have extensions to SQL for doing things like tumbling windows and stuff like that to make this work in practice? And the second is, do you have a notion of time that you present in the IVF, whether it's event time or processing time? And, what does that semantics mean when you deliver that final result? And maybe that'll come in the examples and you could defer the answers then.
It should emerge in the examples, but I can give a high level answer now. Oh, sorry, for everyone. Did everyone hear that? Is it loud enough? Okay, well, so the first part of the question was, do we have these kind of temporal streaming window things, right? We have not yet introduced these as primitives. And my opinion right now is we don't need to, honestly. I think the reason that those were introduced as primitives into most streaming systems is because of these problems. They're kind of like a consequence of not having an elegant solution to these. And hopefully you'll see in the examples how you can implement these windows yourself pretty easily on top of these finalize and final queries. What was the second thing?
Whether there's a semantics for time in the output that you deliver,
Time.
that's
Yeah,
event or processing time.
Right. So all of our semantics are built on top of like the processing or transaction time. But the thing that final and finalize let you do is couple transaction time to an event time. The same way the watermark kind of maps from one to the other. You can think of these as like a hyper generalization of watermarks that give you that mapping. And it doesn't have to be restricted to a single notion of event time. I have an example that shows a join between two time-based streams, and you can actually have a multi-dimensional event time. And using finalization constraints, you can work with those.
Great, thank you.
Okay, so as far as examples, we'll start really simple. I mentioned you want a materialized view type thing where you can drop stuff from the source data. The simplest way to do this is to finalize your, so here, walking through the example step by step, the staging data table is your raw data. The parse data dynamic table is your materialized view. It's really basic. All we're doing is like extracting some fields from a JSON text. But we put this constraint in bold, finalize, insert only. By the way, I'm going to have some syntax sugar here. Anything that comes after finalize can be expressed as a predicate. It's just really confusing. If you see the expanded insert only predicate, it's like it's commit time less than current time. It's like unintuitive, but so we have syntax sugar. But the point is it's all one uniform conceptual framework. And so finalize insert only means this dynamic table is insert only. Once there's a row in it, you can't change it again. And what that means is for the staging data, we'll parse everything and then it won't change again. And that means if we delete something in that last line from the staging data, those deletes won't propagate into the dynamic table. This is like a really simple way of doing this. Obviously, you might want to do updates to the staging data before it's deleted. So you could finalize where the timestamp is within the last 7 days, or sorry, before the last 7 days. So, it's flexible, but the idea is finalization will let you decouple the computation from the source data.
Actually, is that delete query? Is that just?
That's just an imperative DML.
Okay.
But you can
like continuously run.
You would want Snowflake is introducing what we call storage lifecycle policies, which you can like attach to a table and they'll continuously run.
Yeah, okay.
I didn't want to introduce that complication.
It's not a one-shot thing. You're telling the system.
So what I'm doing here is intended as a one-shot thing, just as an example.
Yes.
But
you're also telling it to do
yes,
this.
what the use case demands is exactly a continuous kind of thing. Another kind of thing that I'll defer for later, but might be an interesting detail, is the difference between a deletion and an expiration of data. That's like a semantic difference that only starts mattering once you enter this kind of world, where like delete means propagate, expire means forget.
Why couldn't you put the finalize insert only on the other side of the parentheses?
That's where constraints go. It's pretty surprising.
Okay. No, all right. Okay, so you're treating it as a constraint.
Yeah. So we have this. I mean, I didn't want to put the syntax, but you can name them too. So you can have constraint, foo, finalize, blah, 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 blah.
Okay.
So it's an out of line constraint.
Got
So another example of the kind of thing people want to do is what are called stream table joins or stream static joins. The basic idea here is you have, say you have your Kafka topic, which is just like a bunch of events, and you want to look up something in another table. The kind of default thing with an IVM framework is if you change anything in your dimension table, implicitly, you need to go update everything that ever happened in the Kafka topic, right? And that's not what people want. What people mostly want is an event came in, let me look up the current state and let me send it out. Potential modifications of this are look it up as of the current event time, or maybe keep updating it for some short period of time. And so people have proposed a number of solutions to this involving either bitemporality or system as of time joins. Those kind of work, but they're number one, really difficult to implement with the way that database time travel is implemented, at least in Snowflake. I think also in many other databases. In my opinion, they don't really get at what people are trying to do, which is stop computing stuff at some point in time. And so this, let me walk through the example. We still have like a source table, which is the stream table. There's some dimension table where we're doing the lookup and some common key between them. Remember, we want to get rid of old data in the stream table. Like you can think of some retention policy on a Kafka topic. And so here I've added, some continuous deletion from it when.
Yeah, sorry, finalize.
Oh yeah, that's old. This is an old example.
Okay.
Yeah. Oh, one thing worth mentioning, we haven't finished implementing this. So syntax is subject to change, right? So in the materialized viewer of the dynamic table, we have our query here, which is a left outer join. The stream table looks up against the dimension table on the key. And we have this really interesting constraint here, which is monotonic ascending constraint. Oh, sorry. The name of the constraint is monotonic, and we're finalizing it ascending on the last modified timestamp of the stream table, which means if you look at the order of events in the stream table, once that's computed, and computed means joined against the dimension table, it'll show up in the dynamic table, and we will never update anything for a smaller time again. Does that make sense? And so this very neatly expresses the idea of I'm computing something, I'm joining it, and it's done, right? And we can, the neat thing, just to do a forward hint of the implementation, this starts as a filter at the top of the dynamic table, but you can kind of push this filter down through the query plan so that you never scan anything in the stream that's older than the time that you care about.
So Dan, quick question, and if it's complicated, we can defer it. You're going to use timestamps for this, but since the processing is happening in a distributed setting and the local timestamps where some portion of the stream is getting processed can be different, do you have to worry about timestamps getting synced, or you kind of ignore the small discrepancies that might arise as a result of that?
You have to be extremely careful with timestamps in many ways. For this expiration case, current timestamp, it doesn't matter too much because that's usually like fuzzy. The row last modified timestamp is a new feature in Snowflake, which is the commit time. And so in that case, it's like it has very clear semantics. But yeah, you have to be really careful.
Clock synchronization for that commit time across different records for the same stream flowing in, or you don't worry about that discrepancy too much?
So this timestamp is defined when data is committed into the stream table. And so that happens, it goes through a transaction coordination process, and then the commit timestamp is resolved. And these row timestamps are kind of lazily computed based on that commit protocol.
But stream table could be partitioned, right? And different nodes might be processing inserts into that stream table, and each of that node might have their clocks might be slightly off. Or do you kind of try to keep the clocks close enough and say that's good enough, or do you try to have a more robust notion of what that time means?
Yeah, I mean, I've used a Kafka topic as an example here. And I think, there are ways of connecting it to an actual fully partitioned Kafka style approach. But in this approach, stream table is a Snowflake table, and that has a totally ordered commit log across partitions because, well, Snowflake tables aren't partitioned in that classical way.
Okay, thank you. Appreciate that.
Yeah. And, there are technical trade-offs there in terms of like throughput and like being able to have each partition operate independently. But that's kind of where Snowflake is right now. Any more questions on this one? Oh, yes, sorry.
What I understand from the previous question, we have like a centralized process that assigns total order to every stream event that we receive, right?
So it's not a total order per event, it's a total order per transaction.
Okay, but does that mean it's like a bottleneck or something like kind of single?
It could be, it's not a bottleneck for throughput, but it introduces a trade-off where as you try to make your transactions finer and finer grained, like if you try to do one row per transaction, then yeah, it would become a bottleneck. There are kind of mitigations to this, but I think fundamentally, there are technical trade-offs in any processing system, whether you're leaning toward large batches that do like kind of analytical style processing, or if you're trying to get very, very low latency, and that starts looking more like OLTP. And Snowflake is leaning heavily on the analytical side. So our transactions are totally ordered in that way. But you know, I do think there are reasonable ways of doing this. Like Oracle definitely has a committed timestamp system column. I would be surprised if Microsoft SQL Server didn't have one. So you know, there are ways of doing this lazy timestamp resolution that's totally ordered based on commit. Okay, I guess maybe I should ask here, when should I stop? Because I have a bunch more examples. It's going to go way over time. I'm happy to share the slides. It's almost one.
If you have to go to class, but keep going, databases.
Okay, great. And maybe we can pull Bowei back up to talk about Skew handling. Okay, so this gets at Jignesh's question about Windows. So I guess for folks who don't know, most streaming systems have introduced primitives for doing things like I want to compute the average for each minute or each 5 minutes or something like that. And the reason they've introduced these primitives is because usually you want to window by some event time, like when did the event actually happen, not when did it show up in my system. And in order to do that, you can't actually, you need to tell the system somehow, hey, now this event time is done. You can actually compute this aggregate and get the right answer. And so most streaming systems have a primitive for this. And what I was, in my answer to Jignesh's question, I was saying that finalization lets you kind of tell the system about this without having to introduce these windowing primitives. And so here's an example of that. Here, again, we have a kind of source table. It's called base data with some text. I don't know what the text is there for. Yeah, we don't use the text, but we have a number and a timestamp. And then we finalize where the timestamp column is more than 10 minutes in the past. This is like a really simple kind of hacky approach to coupling the event time to the processing time, but it kind of gets the idea across. And then we construct this windowed aggregate dynamic table that truncates the timestamp to an hour, and then calculates the sum of the value within that hour. So it'll grab it from base table, and then we'll group by the key and the hour, right? And then the last thing we'll add is the system is final column. Let me make sure I don't need to talk about anything else here. Yeah, no, okay. So let's talk about system is final. The basic idea here is we need to know when some result will not change again. Like finalization constrains what can change, right? And if you're doing some really basic transformation on a per row basis, then when a row can't change anymore, the transformed row also can't change anymore. But this gets complicated if you have more than one row feeding into an output row. This can happen obviously with aggregations like this or with joins, window functions, like anything that's not a really simple kind of linear transformation might have a non-trivial relationship between what is finalized in the input and what is final in the output. And so the purpose of this column here, system is final, is the database can actually do this inference for you. In this case, what we will notice is that datetrunc is a monotonic function on time. It's monotonic, but not in like a one-to-one way, but rather it'll map everything that happens in an hour to that hour specifically. And so what we need to do is infer that, change the predicate, right? The predicate starts off as timestamp less than current timestamp minus 10 minutes. And we need to kind of floor that to the nearest hour in the same way that datetrunc does. And it turns out that what pruning does is almost exactly the same thing. Like if you think about how pruning works, when you have a zone map, it gives you like an interval of values that some column could have. And you might have some transformation on that column, like datetrunc. And you need to figure out, you need to infer this interval is totally excluded from this other, it's totally excluded from the interval implied by the filter that I put on this table. And so Snowflake, in order to implement pruning on basically all of our monotonic functions, we implemented that information. You can think of that information as like dependency information, or maybe, actually the way you can think of it is if you have a function with a domain and a codomain, or a codomain and a domain, and you give some interval of the codomain, what interval of the domain could that map to? And vice versa. So you can like propagate these intervals forward and backward through functions. And in order to implement system is final, we can do the same thing where we propagate the interval specified by the finalization through this function to figure out, oh, what will change or what could still change, and then we'll exclude that from the result. So, you know, it's really just a filter where is final. And you'll get everything up to 10 minutes, or sorry, you'll get results up to 70 minutes in the past, basically.
These things are like, are the intervals only finalized or like pushed through whenever, like based on lazy transformation, whenever this is triggered, or just like, no?
So it's done in order to hydrate the is final column. Like this is a virtual column that Snowflake can just synthesize for you. And really what Snowflake does is it'll replace is final with a predicate. And the question is, what is that predicate? And so when that's there, the compiler will see it, and then it'll look down and kind of look at all the finalization predicates and propagate them through every operator using the logic that I just described with the intervals until it arrives at the final predicate. And then it'll just put it there, and it's a normal predicate, and it'll execute it like a normal predicate.
In this framework, it makes sense that so far all the finalization predicates you have shown are some function of the timestamp. Do you see also like users manually marking things as final? Or?
Yes, yeah. So we also have an alter table finalize syntax. And it starts getting really interesting when you do subqueries, because you could do something like you could have a table that keeps track of how much progress you're making, and then have a finalization constraint that looks up in that table what you want to finalize. That is much harder to do this predicate inference, though. And so that's one of the kind of open problems that we haven't tackled yet.
I have the same question.
Okay.
Basically, the predicate after finalized, can it be based on like the runtime value of that table itself? Like, can you do like where max timestamp like PS smaller than max timestamp minus equal?
Yeah, and so we actually have, or we will be introducing syntax sugar for exactly that use case where timestamp is less than max of timestamp. Also, so actually, I already did this. Ascending is syntax sugar for timestamp less than or equal to max of timestamp. And if you want some grace period, meaning like it's monotonic within some or up to some interval, you can subtract something out of that, but we'll have syntax sugar for that too. One of the really interesting open problems here is what can be expressed, what can be inferred symbolically, what can be implemented efficiently. We have like a reasonable set of, we know how to implement a reasonable set of things. And so we're kind of confident enough to move forward, but I think there's like a really interesting space of research here. I suspect full generality is non-decidable or undecidable, but there's some set that's probably really interesting to take a look at.
I mean, so you're a smart person, you're designing to figure things out, but like the average Snowflake customer, can they reason about this kind of stuff? Or
Also an open question.
okay.
So what
this is heavy shit, right? It's like
the inference is
Yeah.
super heavy shit. What we found is finalization, people just get it immediately.
yeah.
Finalization way downstream in a dynamic table that has subtle things, you can kind of walk people through it.
Yeah.
And so that's part of the reason for syntax sugar. We'll have to document patterns and all this kind of thing.
Yeah.
The other, and so is final, is harder to reason about. If so, I can skip ahead. There's some.
This is the other example.
Yeah. So you can diagram this stuff out in ways that feel pretty intuitive. And so what we're planning on doing is adding UI that can be like, oh, you did is final. Here are the transformations we had to do to your predicate, and this is why you got no data.
Yeah.
We'll also add errors. Like if you add is final on something that has no finalization or inappropriate finalization, we'll be like, sorry, this is not really a valid way
Yeah.
question to ask. But there is like intrinsic complexity here. My response to doubters is people have to deal with this anyway, one way or another, as they crank down that latency knob.
Yeah.
They'll have to deal with this order and the decoupling of their data and the processing time. And so, yeah, it's kind of like a tough luck. Like if you really want to get into this ballgame, you have to think about this stuff. And we can do our best to kind of smooth the path.
Like the idea, like that as you dial down the latency requirements, you're essentially getting a whole different class. You're getting the quants.
Yeah, potentially. I mean, I'm hoping that we can grow that significantly,
Sure.
right?
They have a lot of money.
You'd be surprised.
Quants?
No, that other use cases have tons of money too.
Sure, yeah.
Like highly or relatively unsophisticated customers can have solved. I've worked with ones that have solved really valuable use cases, and they just have hoses of money that they can turn on things.
Yeah,
And so those are the people that we're going after.
and it's only a single dimension of time, right? Like,
No, it's multidimensional. Actually, this is exactly that.
oh yeah, cool. Yeah, I see it, yeah.
So there's order time and quote time.
Yep.
If you guys are interested,
So keep going up to.
no, I'm also, the framework is predicate.
Yeah.
And it doesn't even have to be first order predicates. They can be higher order predicates in principle.
Yeah.
And this is where it starts getting interesting. Doing this kind of inference, I don't know what to call it, dependence inference through these operators. I think it's actually undecidable for higher order predicates. Second order predicates, maybe not. Like, I don't know how far we can push this.
Yeah.
So we did Windows. You can do something similar with joins, where actually this is probably a good example because it's 2 dimensions of time. You're doing a lookup between 2 joins, such where the intervals of time overlap, right? And based on those predicates, we can again infer, we can propagate 2 different finalization predicates, right? Like these are, they look like they're on the same timestamp, but these are 2 separate columns on 2 separate tables. And so each table's finalization advances independently. Then it gets joined, those predicates get coupled, and you can do predicate inference to get the output. That kind of couples the 2 timestamps. So I think in this example, I only included 1 timestamp, but I could have included both timestamps. And then the filter, the finalization predicate would also be but 2-dimensional. So yeah, the is final stuff, super interesting, but the finalization actually unlocks a whole bunch of use cases. The backfill control that I mentioned, you can think of it as, what do I not want to change in my dynamic table as being backfill, right? And so if you, here the simple example is, again, you have a base table, you have another dynamic table that gets some fields out of your base table. But you want to add a new field because your JSON your JSON text got a new field, but you know that before a certain time, this field did not exist in the JSON. So by default, if you just replace your dynamic table, it'll try to go back through all of history, parse all of that JSON, look for that field, and null. And you just wasted like a ton of money doing all that backfill. So what you can do is you can finalize the dynamic table at the point in time where you did that changeover, and then set the definition of the dynamic table to a new thing. And when it kind of reinitializes, it'll only backfill stuff after that point. And so this is like hugely powerful for these really big use cases for people who are like relatively cost sensitive. Right now, they're doing all this stuff with like an Airflow tool or a DBT where they manually input these time intervals and they say, I want to backfill on this day and not this day. And like, it gets really complicated and people trip over themselves. The idea is try to make it as simple as possible for them. So that they can just kind of evolve their queries over time.
And I don't think you can use it in Kafka, right? You change like the schema.
Yeah, I don't think, well, so I guess it depends what you mean by Kafka. KSQLDB supports backwards compatible changes, which I think they could swap in a projection, but the thing about KSQLDB is it won't ever backfill.
Okay.
And so they've kind of picked the other side of this, but I'm kind of pushing back against the incremental view maintenance model where you always backfill.
Right. Like, so like case it'd be like a new topic. You're computing everything from scratch for whatever comes.
Oh, I see, a new topic. Yeah, I don't even know what that would look like. I don't think that would work, or that would be supported at all. Yeah, I was thinking like it's the existing topic, and the payloads get a new field. You could deploy a new KSQLDB pipeline on top of that topic, and it would start processing where it left off with the new logic. But it would never backfill.
Got
So
it.
like if you tried to make this change, like, a common thing might be the data team a week later gets a heads up from the apps team that, oh, hey, we added this field. It's really important that we get the data for the last few weeks. So you need to do the backfill,
Yeah,
right?
yeah.
So yeah, those are kind of, I don't know if you noticed, but it matches up with each of the problems that we talked about here, like retaining, propagating, garbage collecting state. Actually, I didn't explicitly mention garbage collecting state, but as part of this, when some result is final, you can also infer everything that was used to compute it and kind of retire that stuff as internal state to the pipeline.
In the sake of time, why don't we wrap it up and then
Yeah.
like, if students have like concluding questions or.
So yeah, this is a new thing. It's being implemented. It's also not a secret. We've actually, I tried to get this standardized with the SQL Standards Committee, and there was a whole, I ended up killing.
Within Snowflake or?
No,
the real one?
the ISO.
Yeah,
Yeah, I chaired that group trying to push us towards standardizing streaming stuff, but we ended up concluding that it didn't, there wasn't a mature enough single answer that everyone can converge to. We kind of temporarily dissolved the group to let vendors come up with their own solutions. And this is kind of what Snowflake is putting its money behind.
I mean, Stonebreaker couldn't get stream SQL in there, so like. That was 15 years ago.
Yeah. So maybe the third time's the charm. Anyway, yeah, any questions?
Give a round of applause.
So we can share these slides. I have a bunch of references to other systems, other approaches, if you guys are interested in digging into them.
Yeah, it would be awesome if you could share the slides. When we put up the YouTube video, we can link to the slides too.
We don't teach streaming or materialized view maintenance. Jignesh, are you teaching materialized views?
No, but I have a couple lectures on streaming in 721 this semester.
Okay. We'll cover like CDC stuff and financial plus later. All right, so Ben did his internship at Snowflake. Bowei did an internship at Snowflake, although that was many years ago. Any questions about working at Snowflake? None, okay.
It's pretty cool.
You can reach out one-on-one, we'll hang out here.
Yeah.
Snowflake is like the Crips and Databricks is the blood, right? So they all like each other. And the data reference, but yeah. We'll cover that in the intro class. Okay, all right, give thanks, yeah.
Great. Thank you guys. Take care.
Thanks, guys.